So today I'm going to talk about Bellman equation and application. I'm going to start from the basic definition of reinforcement learning, and then I will derive some equations called as Bellman equation. Bellman equation is very, very fundamental equations to apply the reinforcement learning into a real problem. Today, I'm going to demonstrate very simple cases of optimization. You remember that in reinforcement learning, we have agent. Usually it is made of deep neural network or CNN or transformer learning. The purpose of reinforcement learning is to train this agent so that he can always make a best decision. And we have environment. It could be a game or robot or AI design or semiconductor designs. There might be many engineering cases where we have to make the best decision. It could be a game or robot movement or AI designs or semiconductor designs. When you are designing your semiconductor chip, probably you have to learn the fundamental principles or physics associated with semiconductor operations. Or sometimes you are learning previous circuit designs and then then you use that again or you modify them. So there are many applications. If you have an agent who make the best decision, they usually decide the actions. If you apply certain actions in the environment, you're gonna obtain reward. When you are designing the foundation model, reward could be performance, power consumption, cost, and there are certain criteria. Designer of reinforcement learning has to define what is reward. And our human value system maybe is reflected onto this reward definition. So when you are designing reinforcement learning, you have the most important criteria is how to define the reward. When our group students are designing the interconnections, they usually use the eye diagram opening and jitter as a reward. By doing the iterations, hopefully this agent can reach to a point, then this agent is very well trained and this agent is supposed to make the best decisions. Because during this training process, we have to have many iterations, including the action decision, and we have to watch the environment, and we have to obtain the reward. usually when we are obtaining the reward, it takes a lot of computations. You remember that training of the transformer model and generative AI takes a lot of computational powers because it has a huge amount of matrix calculations and so on. But in addition to that, in each iterations, we have to apply the backpropagation to the agent to upgrade the deep neural network. So it is kind of multi-loop computing iterations. So training the transform model itself takes a lot of computational resources, but reinforcement learning takes a lot of iterations. Some disadvantage of this reinforcement learning is it takes huge amount of computing resources. In this environment, we have to define state. By having new actions, the state which define the environment will change. At time step t, state is represented by st. Also, we have to define probability distribution. If we apply the action, state of the environment will be changed from S2 to S dash. That probability has to be defined. Sometimes we know this probability, sometimes we don't know this probability. And probably next week, I'm going to give a lecture to train this agent for 2 different cases. Sometimes we don't know this probability. Let's assume I have a coin. If I throw it, we know that flip up and flip down is 50% and 50%. That is the known model. But in many cases of reinforcement learning, we don't know what is the probabilities. So this transition probability is very important concept, and it may be sometimes very confusing, but I will keep moving and moving. So the beauty of this reinforcement learning is that even though we don't know this transition probability, we can find the best optimal solution. And especially in those cases, we are using Monte Carlo method. Probably on Wednesday, I'm going to talk deeply into the Monte Carlo method. So sometimes we don't know where to go. What is the best solution? The answer is we have to try something, and we have to get reward. And trial and error kind of method is also valuable. That kind of method is being called as Monte Carlo method. And each state, we have reward. And also we can define return. So what I'm saying is that in order to apply the reinforcement learning, you have to have a good understanding of this diagram and definition of state, transition probability, return, reward, and return. Based on this understanding, we will be able to derive Bellman equation. In some case, we know this probability, transition probability, that is the model case. Then today I'm going to apply this Bellman equation to find the best optimal solution. In sometimes we don't know this transition probability, then we apply the Monte Carlo method to find the best solution. That is the subject, will be the Wednesday's subject. In order to apply this reinforcement learning, we have to meet Markov property. depending on your actions, your environment will be changed. The property of your environment will be defined by a state. State will be a sequential process S0, S1, S2, ST. Reinforcement learning is useful when you are trying to find an optimal solution who has a sequential decision process. If you have something that is the kind of instant decision process, reinforcement learning may not be a suitable approach. When you have to make let's assume you have a robot arm. From this position to that position, you have a sequential positions. When you are playing Go game, you put a white stone, opponent put the black stone. There's a kind of sequential process that is defined as a S0, S1, S2, and ST. When we are moving this arm, each position may be represented by ST. When we are optimizing deep neural network, probably we can define something, maybe number of layers and number of nodes, activation functions. We may decide sequentially. Then we can define state as a sequentially. And then Markov property means that next state, probability of next state is solely determined by current state. We don't need to know about all the past state. When you are playing Go game, current white stone and black stone position is matter. It doesn't matter how they got up to this point. Positions of the stones at a moment is all the information we need to make a next state, next action. That is the Markov property. If you have environment, game, robot, or AI design, or semiconductor design, you have to define the state. If the state does not meet this Markov property, reinforcement learning is not a good approach. The first requirement is that you have to design the state and action so that next transition to the next state will be totally determined by a current state. Then return means if you make an action, you're gonna get reward. Then you make an action. At that state, you will move to a next state. Let's assume that you have current state, and if you move the next state, at each state, if you make an action, you get a reward. If you make an action, you get reward. As I told you before, a reward is the kind of value system to improve this whole environment. And who is making the action? Agent is making the action. And return is the future summation of future reward. Number one property of this reinforcement learning is that future state will be totally depending on your current state. Second important implication of reinforcement learning is that it is a sequential decision process. Number three is that we're gonna optimize this environment so that we can maximize the return. Maximizing the return means we are looking at the future reward. Future or next future or next future. Gamma is attenuation constant. So another important philosophy of reinforcement learning is that we are putting more importance and value to the future reward, future reward summation. Even though I'm hungry now, even though I'm having hard time today, even though I cannot sleep today, if my future is bright, I would make that direction. That is the philosophy of this reinforcement learning. In that regard, I feel good about reinforcement learning. Especially for young students, when you are deciding your future job or career or husband or wife, even though he is poor, but if he has a potential, I would marry him. That is the return. Yeah, I think that's good. Let's keep moving. Now I'm trying to define some definitions to apply this Bellman equation to solve the best solution. Another things I would like to clearly define at this moment is policy function. If you have a certain state, you have to make an action. That probability is called as policy function. At a state S, the probability of action A is policy function. Sometimes it is known or sometimes it is not known. But when you find the optimal training of agent will make this policy function for example, optimal policy. That is the purpose of reinforcement learning. Another definition we have to define at this moment is that value function is expected return, future reward summation at a state S. Why we have expectation? Because action is actually kind of probability function. So we have to consider, when we are calculating this value function, we have to apply the probability because we don't know what is the action probability. Sometimes it is well known, it is easy to calculation, sometimes it is not known. If that is not known, we have to apply the Monte Carlo method. But anyway, what I'm saying is that value function with a given policy, expected return is called as value function. So this goal of this reinforcement learning is, number one, take experiences by doing the iteration. We have to find the value function. With a given value function, we can obtain best policy function. That is the goal of reinforcement learning. So in order to apply this reinforcement learning, we have to be able to calculate the value function. That is the expected summation of return. Then once we have this value function, we can find the optimal policy that give you the best, that is a policy that give you the best action probability that give you the best return. And so by doing this A and B processes, we will be able to train deep neural network. We're going to apply the backpropagation to train them. So that is the sequence of our class. Let's move on a little bit further. This is very basic definition and understanding of reinforcement learning. From that, I'm going to introduce Bellman equations. Using these Bellman equations, I'm going to give you some optimization problem. It is not easy to instantaneously to understand the Bellman equation, but let me try as much as possible. Value function is expected return. Actually, we have to add all the future reward. But what we found is that this part can be summarized by a single term. if I make an action to next step, I will get a return. And I move the next step, I will move return. But if I step forward, I know what is the return of this new position further. We just add up. This is the future term. It is a kind of chain relationship. So the meaning of this value function is that if we make a transition, our future reward will be this one plus a step next future reward. Let's assume you got PhD degree at KAIST. You may know what is a reward of PhD degree. That is this one. This one is the reward as a PhD student. Even though you don't have PhD degree at this moment, some people respect you because you have 99% to get the PhD at KAIST. Even though you are student at KAIST at the PhD course, still people are respecting you. A few years later, you may get PhD degree and your income might be $100 million, something like that. That is the future reward. You don't need to go through all the ages 30, 40, 50, 60, 70. And from PhD degree to up to 60, you may know what is your future look like. That is this one, this term. So when we are making the iterations to experience what is the best decision, sometimes you don't go to up to the end of your decision or up to the end of your episode. If some people who is your older brother who got the PhD at KAIST and who is working at Samsung, you can look at his life and then you can figure out, oh, that is my best decision. Or you can choose different companies. You don't have to go through all your life to take experience at Samsung or SK Hynix. That is the philosophy of Bellman equation. This second term is a little bit difficult to explain that. This E means expected value. And what actually means is that we have to consider all the probabilities of action. When you join the Samsung, you may go to a DRAM division or system IC division, packaging division, or marketing divisions. If you think a little bit more, we may have different actions, and each path may have different reward. So total summation, you have chance to go to a DRAM division, maybe 30%. System semiconductor division, 30%. So let's consider all the possibilities, 30%, 30%, and each path may have different expected future return. That summation is actually equal to this one. This is a kind of expected representation. This is when you are actually trying to calculate that, you have to apply this one. And you are calculating this action value function. With a given action, you have to obtain the reward and future reward. That is the philosophy of reinforcement learning. If we try to rigorously explain one step by one step by one step by one step, it takes whole day. So I'm going to give you the whole overall picture of these Bellman equations. So in order to give you some easy ideas, I'm going to give you some example. even though you are going to work on semiconductor design, system IC, mobile application IC, or memory, I think major driving force to ask technology innovation or market innovation for the next 30 years, I'm very sure that it will be related to generative AI. So I think it is good to know about generative AI. And also, in many cases, generative AI will be combined with reinforcement learning. So even though these subjects are not very close to or familiar with your current works, I think let's be patient and let's go through. So these Bellman equations will be used when we are trying to find the optimal solution. But the environment could be sometimes very easy, simple, but sometimes environment is very, very complicated. Sometimes we know the probability of action, sometimes we don't know probability of action. And as an educational purpose, I'm going to give you most easiest problem. We have agreed question is, we start here, we end here. What is the best path to reach start to end? This is very simple problem. So we can use the tabular method. Right now, I'm going to use the tabular method, but this is actually very complicated problem. We're gonna use the deep neural network, but for the purpose of the education, we're gonna start with very simple cases. This is actually the environment. Our task is to find the best path from start to end, with a minimal step. In order to define that in the environment, we define reward as a -1. Reward -1. When we are making a step transition from each step, we will add -1. And second one is probability is east, south, west, north. When we are at S6, we can move up, east, north, east, south, and west. We assume that it's a uniform action distribution. Here I said that we don't know what is the policy function. In many cases, we don't know what is the probability. But in this case, for simplicity of understanding of reinforcement learning, we are assuming that transition probability of each movement will be 25%. Uniform action distribution. That is current policy. But after training later on, we will change this policy to make a best decision. Then what we're gonna do is, so at this moment, policy is like that. Uniform transition probability. Right now, in this environment, policy function is uniform. So it will be shown like that graphically. Now, our next target will apply this Bellman equation to obtain this value function. And once we have value function, we will be able to update policy, and by iteration of value calculation and policy function update, we're gonna reach the optimal policy. That is our goal. When we are obtaining this value function, we're gonna use the Bellman equation, especially this number 1, 2, 3, 4. So our next step is how to calculate value function. We're gonna initialize, number one step is we're gonna initialize all the step 0, 0, 0. This is initialization. Initialization of a value function. And by applying those Bellman equation, we're gonna keep update, update, and update. After updation, we will gonna update this policy function, and then we repeat this value function calculation and update of this policy function. We're gonna finally come to the optimal policy, and that is our goal of reinforcement learning. And how are we going to update that? The cell value function of this state will be changed to -1. How can you do that? I will show you the equation. Point 0.25 is action probability. East, south, west, north. Because at this moment, we have all the uniform action probability. As I mentioned before, in some case, we know the probability distribution. Sometimes, most cases, we don't know. But for the simplicity of giving lecture, we're gonna start with a very small size problem. And in a case, we're gonna assume that we know the action probability. That means we know the transition of east, north, south, east, west is equal to 25%. At this moment, if we move one step, action reward will be always -1. And the adjacent value function is 0. That we add, multiplied at 0. This term is actually coming from the future reward, assuming gamma is equal to 1. We move one step, got a PhD degree. What is the future like? Oh, I know that. I come back. So I choose the memory division. What is the future like? We are adding all that together. We don't know go through your career up to 60 or 70. You just look at your older friends of your lab. Then all this summation is becoming -1. We update that. But however, this one is fixed because this is the end. So we repeat S0, S1, S2, Sn, and this value will be updated. And then once it is updated, we apply the Bellman equation again and again. You update this value function, applying the Bellman equation. Now you are using the updated value function table to calculate new value function. When you are updating your value function table, it is gonna use your Bellman equation. At this case, expected case, this probability transition is 4.5%. We can easily calculate using hands. Let's assume that you have this value function upgrade 100% using this. So you have 100 your former students of your lab. You look at his future, you upgrade this table, you look at the another student's future. And last year you updated this table. This year again you call your old friend and what is your life at Samsung? And you update it again and again. After 100 times, this table will be close to this number. So we will obtain this. What this table means, if your policy is random, really random, the number of steps from starting point to reach to end might be around 59 steps. If you go back forth randomly, amount expected number of steps you may have to reach to this one is 60 steps. Here, 30 steps, even though you are very adjacent. Even though you have very good friend adjacent to your table, she may be your good wife, you sometimes look around. You may take 30 steps. It is a very good humor to you, but nobody is smiling. I keep telling to my students in my lab, please find a good wife in the lab. Even though you are staying adjacent, you are looking around internet or something like that. So you may take 30 steps. Then you may be 60 years old finally when you finally find your best wife. Okay? This initialization, update, and this kind of process is kind of experiment. But you are PhD or master course student, you don't have enough time to do all that. So look at around you, okay? Now, let's assume that you updated. Finally, this is optimal value. Then what you can do is that you can update this policy by looking at this most smallest number adjacent to your state is this direction, this direction, this direction, this. From updated table, you can update these policy arrows. This one is really updated policy. This arrow. Initially, we started with random actions. After the training, we were able to derive optimal policy. If you follow this optimal policy, maximum number of steps from here is 1, 2, whatever, 1, 2, 3, 4, 5, 6. Sixth step. If you have wrong policies, you may ask more than 60 steps expected. This is average. Sometimes you may be shorter than 60 steps, sometimes it is longer than 60 steps. But after this, all the training, applying the Bellman equations and so on, we was able to obtain this best policy. If you follow the best policy, you can reach to end by 6 steps. That is the best performance. I think this is the overall picture of reinforcement learning. But for the simplicity of lecture, we are using this very small 4x4 grid problem. Actual problem is million by million, very, very complicated. So table may not be a good solution. Why is that? In this case, we know this probability 25%, 25%. In many cases, we don't know. So we have to try and take experiences. And sometimes we have to make decision. We have to look the history book. What happened in the past, we can learn from that. Even though our present future may not be same as the history book, but still history book is very valuable. And this value function, when we are doing the value function, we have to use the Bellman equation. Why is that? Because when we are defining the return of reinforcement learning, we are putting the future, not immediate reward. That philosophy is transited to Bellman equation. And why it is useful to define this futuristic Bellman equation? Because this is a sequential process. At each stage, we have to determine the best actions. The sequence of best action will result in the optimal policy.